Hello, my BC kids. We are looking at section 15-3 today on something called Taylor series and Maclaurin series. We are stepping away from all the convergence tests for the next couple sections. So for my girl Abby, you can take a break from all those crazy tests that you love so much. Here comes Taylor polynomials. They can be used to approximate other elementary functions such as the sine function or the e to the x function or the ln of x function. These are the most popular. Cosine as well. So sine, cosine, e to the x, and ln of x are all really popular types of Taylor and Maclaurin series. And what happens is you can use the series to evaluate the sine function because of the tangent line. I'll show you what I mean. If you have some kind of function going on, say you have the sine function. We'll use sine since that's what it is. And I want to know what it is at this exact location, that x value. If I can figure out what the tangent line is, the tangent line is going to be a close approximation to where they meet there is going to be a close approximation to what the actual sine is. And I can even go a little bit past that point in an upper direction or a lower direction, and it's still going to be relatively close to the approximation of what that actual value is. So that's kind of the concept behind this. These are kind of like looking at tangent lines. So the first question says, find the equation of a tangent line for the sine function at x equals 0, and then use it to approximate point 2. Is it an overestimate or an underestimate? And that's what we're going to look at. So we know that in order to find a tangent line, you need two things. You need a point, you need a slope, right? We know that from ages ago. So what's the point? Well, x equals 0 is going to be my coordinate, the first part of my coordinate. The y value comes from y equals the sine of x. So this guy is the sine of x, which is 0. So think about it, unit circle. Sine of 0 is 0. And so there's my point. My point is 0, 0. And then I need a slope. Well, the slope comes from the derivative, right? So I need to know what the derivative of f of x is. The derivative of a sine is cosine. And so I want to know what the cosine of 0 is. I'll do it. How am I going to do it? F prime, since I did it that way. F prime is of 0 equals the cosine of 0. And so I'm thinking 0, what's cosine? Cosine is 1. And so I can put together my tangent line. We know it's y minus y1 equals my slope 1 times x minus x1. And that's kind of really a whole lot of nothing, right? It's y equals x. All right, there's your tangent line equation. And then it says, approximate, use that to approximate the sine of 0.2. Well, if this is your x value, and this is your tangent line, we know that y equals x. So if x is 0.2, y is 0.2. They're the same thing. So you're using your tangent line to approximate what this next value is. But it turns out because of your tangent line being y equals x, they're going to be one and the same. Okay, so the last part, is it an overestimate or an underestimate? So you've got to think of, in this case, there's a few things you could do. You could find the second derivative and see if it's positive or negative. Positive would be concave up, negative would be concave down. That would be one approach to this question. But because we know the what the sine graph looks like, we know, we did it over here, if I'm at 0.2, is that graph concave up or concave down in that location? And we can see it's concave down. So sine is concave down at x equals 0.2. Now, where are the tangent lines? Are the tangent lines above it or below it? And the tangent lines are above it, so that means that it's an overestimate. So, overestimate. Anytime, we were talking about this in Calc AB not that long ago, but anytime it's concave down, it's going to be an overestimate, and anytime it's concave up, it's going to be an underestimate, because all of the tangent lines now would be below that curve if it's concave up. All right, so there you go. That's the first thing. Kind of a reminder of several topics that we've talked about in the past. So the equation of the tangent line used in example 1 is called a first degree Taylor polynomial. Taylor polynomials of higher degree can be used to obtain increasingly better approximations of non-polynomial functions with a certain radius from a center of approximation at x equals c. So here's what he's talking about. If I have a center, my center was at 0. That's where they told me to look. And I was trying to approximate close to 0 at point 2. So my center of approximation was x equals 0 for that particular problem. And we only had, in our Taylor polynomial, in our polynomial here, we had one term. But the more terms you take, the more accurate your approximation is going to be. What does that remind you of, right? Those rectangles, the more rectangles you have under the curve, between the curve and the x-axis, the more accurate your integral is going to be. So same idea. The more terms we have, the more accurate our answer. We only had one term, so our answer is not overly accurate, but close enough, okay? So here's the definition of a Taylor polynomial. Taylor polynomials, and this is the difference between Taylor, and I'm going to talk about Maclaurin in just a second. Taylor polynomials are centered at some number, which is different than Maclaurin's deal. Maclaurin's deal is that they're always centered at 0. That's the biggest difference between them. And you'll see the Taylor's pretty much, they're not going to necessarily, if they say the Taylor series centered at 0, it's really Maclaurin, but it doesn't matter. You're going to treat it exactly the same way. So here's how you generate a Taylor polynomial. Taylor polynomials and Maclaurin polynomials are identical to one another, except this guy has, the Taylors have an x minus c instead of just an x. Because technically the center, it would be x minus 0. So this gives it just an x. You'll see it in action if you're not understanding what I'm saying at the moment. But here's how you generate it. You take the first coordinate, whatever that y coordinate is, and then you take the derivative, the first derivative, times x minus c. This one's technically over 1 factorial. We're getting factorials involved. The next one's going to be a 2 factorial denominator. The next one's going to be a 3 factorial denominator. And you're going to keep taking derivatives. So this one's the first derivative times x minus c over 1 factorial. The next term would be the second derivative over 2 factorial times x minus c squared. The next one would be the third derivative over 3 factorial times x minus c cubed, and so on down the line. So here's the general term for it. Okay, so a first degree polynomial is a tangent line of f at x equal at c, and f, whatever the derivative is, this is a notation for the derivative, over n factorial is the coefficient on that term. He's just trying to explain what we just were talking about up here. Now, if it's centered at 0, they're even simpler, because instead of having x minus c, you just have it be an x. And again, you'll see this in action in just a few minutes when we do some problems. But the first term is whatever the y coordinate is. This is the second derivative times x over 1 factorial, which really we know 1 factorial is just 1. Then the second derivative times x squared over 2 factorial. The next one would be the third derivative of x cubed over 3 factorial, and so on down the line. Here's the general term. So here's how it's worded. These are worded kind of fun. Find the Maclaurin polynomial. Well, Maclaurin is centered at 0, so they're the easier ones. We're going to start with one of the semi-easier ones. The Maclaurin, automatically, as soon as you see that name there, you know the center's at 0. So maybe we'll make note of that. This means that the center's at 0 at x equals 0. Polynomial degree 7. This degree tells you how many derivatives you need to take. So this means, this right here, means that I have to take 7 derivatives. What? Remember back in the day of Calc AB when you thought there was only 1 derivative? Yeah, we got to do 7 of them. for this function, the sine of x. Then use the polynomial you generate to approximate the value of 0.1 using correct notation. We're not going to do find the error. That's going to come up in section 15.5. And this is the only question on this packet that asks you for that error approximation. So we're skipping that part of it. We'll save that for 15.5. So what you need to start with, or what are the first 7 derivatives of the sine of x? So I went over to the margin over here, and I started out with the original function being sine of x. And then I just went derivativing, man. I went on a derivative expedition here. The derivative of sine is cosine. Second derivative of cosine is negative sine. Third derivative of negative sine is negative cosine. Got to go more. Fourth derivative of negative cosine is sine. And we're going to start the pattern all over again, right? So once you find those, you're just repeating the pattern. Derivative of sine is cosine. Sixth derivative of cosine is negative sine. And shoo, just enough space here. Seventh derivative, negative sine is negative cosine. All right, so what are you going to do with these crazy, with all these crazy derivatives? We're going to put them into the polynomial. Excuse me. Before we do, here's what we need to do. We need to now evaluate each of these things at, I'm going to put a different color, I'll put it here, at x equals 0. We need to now evaluate each of these derivatives at x equals 0. So I change my color. The sine of 0 is 0. I'm just going to put it next to it. The cosine of 0 is 1. The negative sine of 0 is back to 0. The negative cosine of 0 is negative 1. So again, and then it's just going to be the same pattern, right? So it's going to be a 0, a 1, a 0, and a negative 1. And what these are going to do is be the coefficients. These red numbers that I've got there, they're going to be the coefficients as I generate this. It's a Maclaurin. As I generate this polynomial. So let me show you how it works. They call it a polynomial of 7th degree for x. Sometimes you'll see this as t base set, like with a subscript of 7 and x, Taylor series. Or you'll see an m with a little 7. Really, it's a polynomial. So let's just keep it as p. It's a polynomial that you're generating. So the first term comes first, right? What's that y value? What is it equivalent to? And we say 0. That's this number right here. And then I have a plus. And then I have a 1. F prime of c is 1. So I have a 1. And then I have times, I'm going to put it this way, 1 over 1 factorial x to the first power. And then I have plus. Now I'm going to the next one. That's this guy. He is going to be 0 over 2 factorial x to the second, because it's the second derivative. Next one's going to be minus. Or it could be, well, let's leave it as plus. We'll put the negative 1 here. Negative 1 over 3 factorial x cubed plus 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth. Am I going to have enough space? I don't know. Plus 0 over 6 factorial x to the sixth plus, I'm going off the page, I'm going to have to go this way. Okay, plus, last one is a negative 1 over 7 factorial x to the seventh. There's a 7th degree, right? Now you're going to clean it up. That's your last job here, is clean it up to figure out this polynomial. You don't need the 0. And 1 over 1 is 1, so this is just an x. So my first term is just an x after all that. So that takes care of the first two. This one, 0 over anything is 0, so it knocks the whole term out. This one's a minus, so it's going to be minus this guy. So I have 1 over 3 factorial. Now you can choose to leave it that way. You could multiply it out. Remember, that means 3 times 2 times 1, so it would be equivalent to 1/6. X cubed. The 0 again gets knocked out, so I don't have a fourth powered term. I go to this guy, he's plus 1 over 5 factorial x to the 5th. And again, you could write this out as whatever 5 times 4 times 3 times 2 times 1 is. The 0, the 6th power gets knocked out, and now I'm left with the 7th power. And there it is. There is my 7th degree Maclaurin polynomial for the sine function. Are we done? Find the Maclaurin, degree 7, we got it. Use that to approximate the value of sine of 0.1. Now notice 0.1 is very close to 0. They wouldn't ask me to figure out what it is far away. They can only ask me values close to the number that I'm centered at. So I want to know what p sub 7 of 0.1 is. So what do? I go to my calculator and I say, all right, 0.1 minus 1 over 3 factorial times 0.1 cubed, 1 over 5 factorial, 0.1 to the 5th, minus 1 over 7 factorial, 0.1 to the 7th. And I go to my calculator and I say, happy calculator, what does this come out to be? And for the sake of our time, I know you know how to put things in calculators. You should get a value somewhere close to 0.0998. And there it is. You just generated a polynomial. Now, if I only had a single term, if I only had just like we had up in the first example, example 1, that's not as close an approximation as what this one would be with 4 terms. So you can see there's a difference between the two. This is going to be more accurate. All right, next page. There's a lot of examples to this section, but we'll see if we can fly through them relatively fast. This one, I think the numbering got funky on this one. On this page, I'm just looking at this now. Yeah, he went example 1 and then example 3, and now we're on example 4. So anyway, example 4. We'll go with the flow. Example 4 says, list the first 4 non-zero terms and the nth term for the Maclaurin series for f of x equals the sine of x. Well, didn't you just do that? Didn't we just do the Maclaurin series for the sine of x? So we know, this is from example 3, we know what the polynomial looks like. The first term is x, then it was minus, technically it looks like this, x cubed over 3 factorial plus x to the 5th over 5 factorial, right? I'm just writing it without those so that it's a combined one single fraction. Minus x to the 7th over 7 factorial. And I have to come up with, the real question here is what's the nth term? Now, remember, and this, I know this kind of confused Olivia a bit, but this is when n equals 0. This is when n equals 1, 2, and 3. And the only reason you want to do that is because this has to be in terms of n's, right? You have to have your polynomial ready for n's. So the question is, how can I generate, like, what would the general term be, the nth term, if I look at it with these values? What's happening with this thing? So one thing I notice is that my signs are alternating. If my signs are alternating, then you know you need a -1 to the n power or something like that. Now we'll go back and check that nth power, right? Because sometimes it's n plus 1, sometimes it's a little bit different. But for now, let's just put the n there because we know that we have an alternating power. We know we have x's to some power. And funny enough, whatever this power is happens to be what the denominator is, right? Because the power is matching the denominator. So whatever we come up with for the power formula on this is going to be the same thing that's generated in the denominator. All right, so is it x to the first? No. And I'm going from a 1 to a 3 to a 5. You can see it increases by 2 each time, right? So let's try maybe a 2n. And see if that works to get these values of 1, 3, 5, and 7. If I do that, if n is 0, 2 times 0 is 0, that would be just x. it would be just x to the 0, which would be 1, not x. All right, same with this guy. If I put a 3 in there, that would be x to the 6th. Yeah, that's not going to work for where we're at. So I'm looking, I'm sorry, if it's n equals 1, 2 times 1 is 2. So it would be x squared. That's not what I want. But I want one more, right? To go from 2 to 3, what if it's 2n plus 1? Will that work? If n is 0, 0 plus 1 is 1, x to the first is x. If n is 1, 2 times 1 is 2, plus 1 more is 3. Ooh, I think I'm on it. If n is 2, 2 times 2 is 4, plus 1 more is 5. This is it, 2n plus 1. That's the one. And this power here, the nth power, works also for our alternating signs. Because if this is 0, this would be a positive 1. If this is 1, this would be a negative 1. If this is 2, it would be a positive 1. So this just to the nth power works. And we already said whatever this power is the same thing that our denominator down here is. Oh, one more thing. Factorial, right? It's in a factorial form. So we listed the first 4 non-zero terms, 1, 2, 3, 4, and the nth term for the Maclaurin series for sine of x. All right, number 5. Find the Maclaurin series polynomial of degree 7, another 7 derivatives. That means for the cosine of x, and use it to find the first 4 non-zero terms and the nth term. So now they're combining example 3 and example 4, but they want us to do it for the cosine function. So I need to first start with the first 7 derivatives of the cosine of x. So my function is the cosine of x. And I'm going to go derivativing it again, and it keeps, once you get the first few, it repeats itself. So cosine of x, derivative of cosine is negative sine. Second derivative, the derivative of negative sine is negative cosine. Third derivative, the derivative of negative cosine is sine. Fourth derivative. Notice the notation too. You remember that? How it changes after you get to the third derivative. From there on, it's just they just toss a number up there. Derivative of sine is cosine. Fifth derivative. Derivative of cosine is negative sine. And again, I'm now just repeating the pattern. Sixth derivative is negative cosine. And seventh derivative is sine. And then I need to evaluate it at the center. And in our case, our center is 0. Because it's a Maclaurin, I automatically know that the center's at 0. All right, so cosine of 0 is 1. I'm going to put it in the wording there. The negative sine of 0 is 0. Negative cosine is negative 1. Sine of 0 is 0. Cosine at 0 is 1. And then we're just repeating. So this is a 0, this is a negative 1, and this is a 0 again. All right, let's generate the polynomial. Polynomial of 7th degree is, take the first guy, he's a 1, plus, and then it's 0 over 1 factorial x to the first. And then it's minus. Now you could leave this as a negative 1, but I think you got the idea with the negative here. So 1 over 2 factorial x to the second. Then it's plus 0 over 3 factorial x to the third, plus 1 over 4 factorial x to the fourth, plus 0 over 5 factorial x to the fifth, plus 1 negative, or I'll distribute negative, so subtraction, minus 1 over 6 factorial x to the sixth, plus 0 over 7 factorial x to the seventh. Oh, you can barely see me there. We smushed it all in. And then we're going to clean it up. I have a 1. This zeroes out. I have a minus 1 over 2 factorial. 1 over 2. Yeah, we'll leave it with factorial. X squared. This zeroes out. Plus 1 over 4 factorial x to the 4th. This zeroes out. Minus 1 over 6 factorial x to the 6th, and the 7th term zeroes out. So here's what I've got. And my job now, so we generated the polynomial, and you'll notice that this versus the sine one, they're extremely similar to one another. Sine has all the odd powers, where cosine has all the even powers. So that's something to take note of. It'll come up later in other sections. But Mr. AP assumes that you will memorize the sine function and the cosine function, what their Taylor or polynomial looks like, what their expansion looks like for a Maclaurin or Taylor polynomial, whichever. Okay, so the next piece is use it to find the first 4. We did that. Find the nth term. Plus, dot, 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 plus. And we've got to figure out what the nth term is. All right, so this is when n equals 0. I get a 1. When n equals 1, 2, 3, do the signs alternate? And you say, yep, yep, they do. So, -1, oh, not in blue. Let me go green and gotta be consistent. All right, so we know it's alternating signs, -1 to the n. We're going to leave it as an n. We'll come back and check it. We know we have an x to some power. And whatever that power is going to be the same thing as what our denominator is factorialed. So let's check it out. My power, in order to get this 1, must be x to the 0 power. Right? In order to get a 2, if my n is 1, it might be it could be an n plus 1. That would give me 2, right? But n plus 1 here would give me a 3. That's not what I have. So n plus 1 is not going to work. But if I look at this, kind of compare it, 1 goes to 2, 2 goes to 4, 3 goes to 6. They're all being multiplied by 2. So let's try a 2n and see if that'll fit. If I have a 0, this would be 2 times 0 is 0, x to the 0 is 1, and this is my 0 term, so this is a positive 1, and that would fit for this deal. Let's try this middle guy. If it's 2, if n is 2, 2 times 2 is 4x to the 4th. Okay, cool. -1 to the 2nd is positive. Okay, it should be. And so that works. And whatever the power is, we already said, is what our factorial is. 2 times 2 is 4. That's my factorial. So there's your general term. I know it's kind of a game of playing around with these things a little bit to guess and check, but that's the story. Example 6. Find the Maclaurin polynomial. Again, Maclaurin is centered at 0 of degree 4. Oh, thank God, we're only going 4 derivatives. So there's a couple things to take note of in their directions. This tells you that the center's at 0 because they said Maclaurin. This tells you that you have to go to the 4th derivative for e to the x and use it to find the first 4 terms in the nth term. Okay, well, my function is e to the x. Now, this is pretty. Watch this. First 4 derivatives. F prime of x. Well, what's the derivative of e to the x? E to the x. What's the derivative of e to the x? E to the x. What's the derivative of e to the x? It's e to the x. Did I go there? 1, no, function, 1, 2, 3. Here comes 4. 4. Okay, second thing is evaluate it at 0, x equals 0. So at x equals 0, e to the 0 is 1. E to the 0 is 1. E to the 0 is 1. 1 and 1. All right, let's generate the polynomial. I want P4. I have a 1 plus 1 over 1 factorial x to the first plus 1 over 2 factorial x to the second plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth. All right, there we go. There's my fourth powered degree 4 polynomial for this. Now I can pretty it up. Let's see if we can clean it up any here so that we can figure out that nth term. 1 plus, this is 1 over 1 x to the first, so it's just x. This one's going to be, I don't know that I can pretty up any of the rest of them. For the sake of coming up with that nth term, I'm going to leave them in their factorial mode here. Okay, so again, just to think about the nth term, this is when n equals 0, 1, 2, 3, and 4. Oh, interesting. Notice what the powers are, right? And the powers are the same as the factorials. So this one might be easy peasy lemon squeezy to figure out. The signs do not alternate. I don't need the -1. And my x is going to the same power as what the n is. So x to the n over, and my factorials are identical to the n's as well. And so that's going to be over n factorial. How about that one? That was nice. All right, they finish with a nice one before they go to Taylor polynomials. Taylor polynomials are generated the exact same way, but you're not just going to have an x, you're going to have a quantity, a parenthesis of x minus whatever the c value is. I'll show you what I mean. Example 7. Find the Taylor polynomial of degree 4. We have to go 4 derivatives, centered for ln of x, centered at 1. That means that each of your groupings this time, you have a grouping where your center's not at 0. It's going to create this x minus 1 grouping in these places where you have x's. So that's going to be the difference with these Taylor polynomials because the center is not 0. So we're going to find the Taylor polynomial for ln of x and then use it to approximate 1.1, ln of 1.1. And again, they can't ask you to evaluate it at the ln of 3.5 because you're centered at 1. That would be way too far away. So they got to only give you values that are close to wherever the center is. All right, so let's go for derivativing over here. We need 4 derivatives for the ln of x. My function is the ln of x. I'm going to go 4 derivatives. First derivative of ln of x is 1 over x. Second derivative is, this is like x to the -1. So the -1 would come down, and it would be x to the -2. Right? And then the next one, third derivative, this would be negative x to the -2, comes out to be 2 over x cubed. The negative create a positive. And then the fourth derivative would be like 2x to the -3. That would create a -6 over x to the fourth. I know you know how to find derivatives, so I kind of did that fast, but all right. Now I need to evaluate it at x equals 1 this time. So this one is at x equals 1, where all the rest of them so far have been at x equals 0, because that's where the center was. It's always wherever the center is where you're evaluating these first derivatives. So the ln of 1 is 0. 1 over 1 is 1. -1 over 1 squared is -1. 2 over 1 cubed is 2. And -6 over 1 to the fourth is -6. That wasn't bad. So let's generate the polynomial, see what it looks like this time. So this one is a p polynomial of 4. p sub 4. Again, sometimes you'll see this as a t for Taylor polynomial. It doesn't matter, it's still a polynomial. So we're just going to keep it at p. P sub 4 of x. First term is 0 plus 1 over 1 factorial, but instead of you using x, you're using x minus 1 to the first. Then it's going to be minus 1 over 2 factorial, grouping x minus 1 squared. This x minus 1's in my way. I'll go this way with this. Fix my notation. Okay, and then I have plus 2 over 3 factorial x minus 1 cubed. And then minus 6 over 4 factorial x minus 1 to the 4th. So we have a 4th degree polynomial for the ln of x centered at 1. We got that. This is what it looks like. I guess we can kind of prettify it a little bit. Forget the 0. 1 over 1 factorial is 1, and x minus 1 to the first is just x minus 1. All right. This next one, 1 over 2 factorial, we can write that as, and it's negative, 2 factorial, 2 times 1 is 2, so this would be like x minus 1 squared over 2. And why am I simplifying this out more so than I did the others? Only because I have to evaluate it at 1.1, and you'll see when we do this, it's going to make your math a little bit easier to put in the calculator. By the way, these are always calculator questions when they ask you to do this kind of stuff. They're not going to make you do it in your head. So you've got 2 over 3 factorial, this is 3 times 2 times 1, this is 6. 2 over 6 gives me 1/3. So I have this next one is plus x minus 1 cubed over 3, 1/3. This one is 4 times 3 is 12. 12 times 2 is 24, so 6 over 24 is 1/4. So, ooh, look at this. This makes it nice if they ask me for the general, right? You can kind of see how this is going. They didn't ask me for the general. But this one will be x minus 1 to the 4th over 4. All right, they want to know this time what's the approximation for the ln of 1.1. Now it's going to be an approximation, and it is the same value you get if you put a 1.1 into your polynomial. And so if I put 1.1 minus 1, I get 0.1. This one would be 1.1 minus 1, 0.1, squared over 2. 0.1 squared over 2. And again, every set of parentheses, you're going to have a 0.1 cubed over 3. And a 0.1 to the 4th over 4. Go to your handy-dandy calculator, and here's what you get. 0.0953. All right, that takes care of example 7. We're almost done. Examples 8 and 9, we'll call it a day. This example 8 is probably one of my favorite ones that they ask because it is easy peasy. They're giving you the answers, so you don't have to find all the derivatives. So this is a question where the derivatives are all given in the question itself. All right, so suppose g is a function that has which has continuous derivatives, and that g of 2, your first function, gives you a value of 3 out. The derivative, first derivative, gives you a negative 4 out. The second derivative gives you a 7 out. The third derivative gives you a negative 5 out. Write a Taylor polynomial of degree 3 for g centered at 2. Well, centered at 2 means that you're not using x, you're using x minus 2 as your grouping. But what they've done for you, let me go back and show you from the last problem here. What they did for you is they gave you all of these values. they gave you what it was at g of 2, at g prime of 2, at g double prime of 2, and at g triple prime. So they gave you these values that are going to become your numerators in here. And so it makes it really simple. So I'm taking a polynomial of degree 3. The first term is whatever the y value is, so 3. Plus, actually, well, I'll leave it as a plus. A negative 4, that's this guy. So these are the values you're using right here as your numerators. So the next term would be 4 over, remember the factorial, it's a first one, so it's a 1 factorial. Your grouping is x minus 2, and your power is a first power. All right, next one. 7 is your numerator, 2 factorial is your denominator, x minus 2 is your group squared, plus negative 5 over 3 factorial, x minus 2 grouping to the third power, and you have just generated a third degree polynomial, power 3. Let's clean it up. 3 minus 4 over 1 is 4 times x minus 2 plus, and I guess there's not a whole lot more you can say about these guys. You could multiply out the factorials, you could leave them as factorials. There's really no right or wrong for that, but we'll just make it pretty because this is a pretty simple one. 2 times 1, x minus 2 squared, minus 5 over 3 times 2 times 1 is 6. X minus 2 cubed. And there it is. You just generated it. They gave you all the work right there. So they did most of the work for you, just giving it to you in those answers. Okay. Last question, number 9, but of course it has to have 4 parts, right? Number 9. Let p of x, here's your polynomial, be this. It's a 4th degree Taylor polynomial centered at 4. We can see that because it's an x minus 4 grouping, and we can see it's a 4th degree. Assume that f has derivatives of all orders for all real numbers. Find f of 4 and f triple prime of 4. All right, so f of 4 is whatever the first term is. That's, remember when we did all of our derivative things, that was the first one. So I know that f of 4 is the first term, and that would be, the first term was 7. So I'm going to say f of 4 equals 7. And then it says, find the third derivative. This is the first derivative, this is the second derivative, this is the third derivative. So I know that negative 2 is my coordinate. But I also know that to get negative 2, it had to be some number. Maybe I just want to call it, I don't want to use x or n. Let me use, I don't know, b. Just a letter. That negative 2 has to equal that over, what's the factorial for a 3, right? 3 factorial. So negative 2 is what it comes out to be in a simplified version. I want to know what that numerator would have been. Well, 3 factorial is the same thing as 3 times 2 times 1, so that's 6. How do you solve for my variable? You would cross multiply and you get b equals negative 12. And so that means that f triple prime of x of 4 equals negative 12. So you can't just take the number, because you can't forget that it actually has a factorial, a denominator involved in it. Negative 2 is what you get after you simplify it. So you've got to go backwards and figure out what that actual value was that was there in the first place. So negative 12 over 3 factorial, negative 12 over 6, gives you the negative 2 that is the coefficient that they're talking about right there. All right, second one. Write a second degree polynomial for the derivative about x equals 4 and use it to approximate the derivative at 4.3. Well, that means that I've got to take the derivative, p prime of x. So I've got to go back and take the derivative of each piece. So you're just taking it term by term. Don't make this too crazy. The derivative of 7 is 0. The derivative of 3x minus, you could do this a couple different ways. Let's go with the chain rule. So it's to the first power. 1 times 3 is 3. And then I take this to 1 less power, so that just disappears. So this is just a minus 3. I start with the chain rule because chain rule is easiest for the rest of these. By the way, chain rule says it's times 1 in the, you know, you got to go and also multiply by what the derivative of the group is, but the derivative of the group is just a 1, so you don't have to worry about it. 2 times 5 is 10. Take this to 1 less power. So plus 10 x minus 4 to the first. I'll just leave it as an x minus 4. Next one, 3 times negative 2 is negative 6. Bring the grouping to 1 less power. Squared. And what do they say they wanted this? A second degree. So yeah, we're done at this place. We only need to go to the power of 2. And then they say, okay, we'll figure out what it is for p prime. Use it to figure out 4.3. Approximate that. Well, 0 is 0. I don't care about that. Minus 3 plus 10 times 4.3 minus 4 is 0.3. Minus 6 times 4.3 minus 4 is still 0.3 squared. And so again, you go to your handy dandy calculator and you calculate what that is. It will be a negative 0.54 or so. So sometimes they're going to ask you to take derivatives. That was the idea. Sometimes they're going to ask you to take integrals. That's part C. Part C says, okay, now take this thing, write the 4th degree polynomial for g of x equals the integral of f of t dt about x equals 4. So we're still centered at x equals 4. But what they want you to do, and we already have the fourth degree polynomial. They gave it to us up in the directions. I know it kind of is off my screen. But you already have what the polynomial looks like. And so what you're going to do is you're going to integrate. What they're asking you to do is integrate each term. Where back in C, they wanted you to find the derivative of each term. It's almost like you treat them individually. It's kind of easier with derivatives, of course. Derivative of each term. All right, now let's think about what this looks like when we integrate each term. That means I'm taking the integral, and this is going to be a lot of writing, so go far left, of 4 to the x, because that's what they said, 4 to the x, they're my bounds, of 7 dx. And then I'm going to add that, or subtract actually. The next one is the integral from 4 to x of 3 times x minus 4 dx. Then I have a plus the integral from 4 to x of 5 times x minus 4 squared. And then I have the integral minus 2. I'm sorry, the integral, I should put the 2 inside for now. Keep it consistent. 4 to the x of 2, x minus 4 cubed. Now they said a fourth degree. Now this is an interesting, do I need to take the next term or not? Do I need to take the x to the 4th term? Remember, you're integrating. So what happens to your powers? Your powers are going to go up a power. And so if that's the case, if it's up a power, then you're done at a cube, because when you take that cube and you add the power on like you do when you integrate, you're going to be at the 4th powered thing that they wanted. Okay, so when you're integrating, take one less. It wouldn't be wrong for you to take the next term. It's just more work than you have to do. That's not what they're asking for. All right, so here's where it gets a little bit weird. Well, at least the first term anyway, I think. If I have this integral of 7, and if I take the integral of the 7, it would be like taking this 7, and then f of b minus f of a for this guy would be x minus 4. 7 times x minus 4. And by the way, what I'm looking for here is finding the integral from 4 to x. What I'm putting together is the integral of 4 to x of p of x. So think of this first term. It's kind of goofy, but it's an f of b minus f of a. The rest of these are relatively nice. It's going to be minus, for the minus. The 3 comes out of the integral. And if I take this grouping to one more power, right, power rule, take the group to one more power and divide by that power. That's what you're doing with these guys. Next one's going to be plus. You've got a 5. Take the group to one more power, divide by the power. Last one, treat it the same way. 2 times x minus 4 to the 4th over 4. I guess you could call that 1/2, but there you go. So write a 4th degree Taylor polynomial for the integral of that function. And there you go. That's what it would look like. All right, last one. We're almost done. Can f of 3, we kind of talked about this earlier, can f of 3 be determined by the information given? Justify your answer. Well, where's this thing centered? This thing's centered at 4. If you're centered at 4, then 3 is way too far away for you to make an approximation that would be accurate. You could make an approximation, but it wouldn't be very accurate because you're too far from the center. And so that's what this is asking you. And you say your answer is f of 3 can't be determined I would say because it's too far from the center. Center of x equals 4. The further away you are, the less accurate your approximation is going to be. 3 is way too far away. Okay, that finishes our notes for the section. Now, here's the story with the homework. Let me just show you. The homework page for part A looks like this. You know enough to do numbers 1, 2, 3, and 4. 4's on the next page. But numbers 5 and 6 are optional. 5 and 6 are optional because they go back to reminding you of how to do things we learned previously. So 1, 2, 3, and 4 are the actual homework for this. I did include the answers for the optional problems if you choose to do them. They are on our classroom page. So you're just doing numbers 1, 2, 3, and 4. And again, that's on our classroom page too. So I will see you in class, and I hope you have a great break. Bye.